We are now going to talk about equivalent vectors. We'll talk about what they are, and then we'll talk about how to determine whether or not two vectors are equivalent. So basically, two vectors are said to be equivalent if they have the same magnitude and the same direction. Okay, so if the length of the arrow is the same and the direction of the arrow is the same, then they're said to be equivalent. So wherever they start in the plane, if they have the same length and the same direction, then they're said to be equivalent vectors. Okay, so what we got to do is we're going to find the length of the vector, and then we'll find the direction of the vector. So for the length of the vector, we're going to use the distance formula, because that tells me how long a line segment is, and I got the two ordered pairs there, and that'll be the magnitude. So the distance formula gives me the magnitude of the vector, and then for the direction of the vector, we'll find the slope. Okay, they're both going in this direction. If they both have the same slope, then we'll know if they have the same direction. Okay, and again, we got the two ordered pairs, so it's easy to find the slope. Okay, let's start with the magnitude. So to write out the magnitude, I'm going to put it in absolute value signs. So this is vector AB with an arrow pointing backwards. Okay, so what you do when you write out a vector is, if you write it out in terms of the two letters at the beginning and at the end, then you start with the terminal side, the end of it, and then the beginning side, and then you draw the arrow backwards. And that is vector AB. It means it's a vector going from B leading to A. Okay, that's just the convention for doing it. And now we're going to use the distance formula between these two ordered pairs. Okay, so difference in the x values, that's -3 minus 2, that quantity squared, and then the difference in the y values, 2 minus 4, and that quantity squared. And then you take the square root of this. Okay, so -3 plus a -2, that's -5 squared, and that equals 25. And then 2 plus a -4 is -2 squared, and that equals 4. And so take the square root of that. So now we can add those together, and we got the square root of 29. Okay, and if you wanted to, you could write that in a decimal form to get the idea of what the length is. So the square root of 29 is approximately 5.4. Okay, and so, but when you're actually working with vectors, you usually leave it as a square root, because that's the exact form of it. So now, what about for vector CB? We'll take the magnitude of this now. So we got -1 minus 4, that quantity squared, plus -3 minus a -1, and that quantity squared. Okay, -1 plus a -4, that's -5 squared, so that's 25, plus, and -3 plus a +1, that gives me -2 squared, so that's 4. And we see then that these both have a magnitude of square root of 29. So they have the same magnitude. So now we check to see if they have the same slope. So for this first one, difference in the x values, -3 minus 2 over 2 minus 4. So this is -5 over -2, or 5/2. And then this one is -1 minus 4 over -3 minus a -1. And again, this is negative 5 over negative 2, which is 5 halves. So they have the same slope. Okay, and they are going in the same direction here. So they have the same magnitude, they have the same vectors, or they have the same slope. So these are equivalent vectors. Okay, these are equivalent vectors. Okay. Now let me actually give you kind of a shortcut. Okay, what I'm going to do here is I'm going to teach you about the component form of a vector, which we're actually going to talk more about in the next section. And so, but I think this is if you're given this information, if you're given ordered pairs for the endpoints of the vector, like you are here, and you want to see if they're equivalent, then what I would do is I would get the component form of each of these vectors. So what do I mean by that? So vector AB, okay, the component form, so I'm going to use a square bracket like that, and the component form is going to be the difference in the x values, so negative 3 minus 2, and then comma, the difference in the y values. And so that would be 2 minus 4. And what I get here is negative 5 and negative 2. Okay? This is known as the component form of this vector here. Okay? And so what about CD? Basically, two vectors are equal if they have the same component form. Okay? So negative 1 minus 4, and then negative 3 minus a negative 1. And so this is negative 5, negative 2. Okay? And so they have the same component form. They're really equivalent vectors. Okay? So what is this component form? It's basically, this first one is how much horizontal change is in the vector from the beginning here to this point here, and then this one is the amount of vertical change. So this is going back 5, down 2. Okay, so this one's going back 5, down 2, and so they're the same vector. They both go back 5, down 2. And in fact, what we would say here is I'm going to go 1, 2, 3, 4, 5, down 2, and then I'm going to draw this vector here, and we could just call that V or whatever, and vector V is negative 5, negative 2. Now all three of these are equivalent because this would be 0, 0 over here, so and this here is negative 5, negative 2, right? So if you took negative 5 minus 0, negative 2 minus 0, you would of course get this component. So all three of these are equivalent vectors. They go in the same direction. They have the same length. And what we would say is this is kind of the vector. This is this vector here put in standard position. Okay, so the vector in standard position is taking and moving it to the origin. Okay, and then finding the component for the tip. Here, the initial side 0, 0, the tip then is the component form of the vector. And oftentimes this is very helpful because if you're dealing with different vectors, different forces, where they're at in the plane doesn't necessarily matter. You just need to know, if you have like the wind speed and the airplane speed, you just need to combine, you need to find the resultant vector, and you can place them at the origin and deal with the components, and it simplifies things quite a bit. So there's some freedom with being able to move these vectors around in order to solve different problems, and you'll get a feel for that. Okay, so this whole thing here, this is called the component form. Component form of a vector, and we're going to use that. We're going to deal with this more in the next section. Okay, so that's equivalent vectors here. So in the next video we're going to talk about adding vectors.